This presentation covers the history of hydrologic changes in the Everglades, current conditions, and their ramifications for ecosystem restoration. Water is the lifeblood of the Everglades and the South Florida economy. The Everglades watershed begins in the headwaters of the Kissimmee River and flows southward 70 miles into Lake Okeechobee. Historically, a shallow sheet of fresh water flowed for 100 miles from the southern edge of Lake Okeechobee to Florida Bay. The water moved slowly over the extremely flat Everglades landscape through the wetlands into coastal bays and estuaries, creating a river of grass. Today, this diverse mosaic of landscapes and seascapes supports a complex natural and man-made ecosystem linked by flowing water. Human development altered the South Florida landscape. Drainage projects in the greater Everglades watershed began in the Kissimmee River Basin and the upper Caloosahatchee wetlands in the 1880s. By the 1920s, 6 major canals redirected water from Lake Okeechobee to the Atlantic and Gulf coasts. During the 1930s, a levee system was constructed around much of Lake Okeechobee, and by the 1950s, the northern Everglades were diked and drained to form the Everglades agricultural area. By the 1960s, the central Everglades were enclosed with levees forming 5 water conservation areas. The overall goal of this project was reclaiming the swamp to promote agricultural and urban development. By the early 20th century, this combination of land use and water management actions disrupted the Everglades' natural water flow and ecosystem functioning. By the 1980s, the adverse impacts of drainage and development in South Florida were well recognized. The state of Florida and the federal government began major land acquisition programs and several localized restoration projects in the Kissimmee River and southern Everglades. In 1996, Congress directed the U.S. Army Corps of Engineers to conduct a reevaluation of the Central and Southern Florida project for flood control and other purposes. In 1999, the Corps completed the CNSF restudy, Final Integrated Feasibility Study and EIS, laying out a plan to reverse the major unintended impacts to the South Florida ecosystem attributed to the Central and Southern Florida project. The restoration actions were designed to address landscape-scale alterations from widely fluctuating water levels in Lake Okeechobee and excessive flows to the northern estuaries to detrimental water depths and hydroperiods in the Everglades and insufficient flows to the southern estuaries and degraded water quality. This listing of adverse water management changes in South Florida will be used as our outline to compare the pre-drainage and current conditions and describe restoration guidelines. Lake Okeechobee receives runoff from an upstream watershed covering over 4,000 square miles. The pre-drainage average annual inflows based on the Natural System Regional Simulation Model were approximately 2.2 million acre-feet, which included flows from adjacent marshes upstream of the Caloosahatchee and St. Lucie estuaries. Average annual outflows from the lake were approximately 1.8 million acre-feet and predominantly southward to the Everglades. Pre-drainage lake levels were estimated to fluctuate between 19 and 22 feet NGVD based on rainfall conditions in the watershed. The boundary of the lake varied seasonally as the adjacent wetlands were flooded and receded. Lake Okeechobee still receives the runoff from the upstream watershed covering the same 4,000 square miles, but the lake is cut off from the adjacent pre-drainage marshes by the Herbert Hoover Dike. Current average annual Lake Okeechobee inflows based on the regional simulation model are approximately 1.9 million acre-feet, and the reduction is likely a reflection of the redirection of flows from the Caloosahatchee and St. Lucie marshes. Average annual outflows from lake are approximately 1.4 million acre-feet per year, with regulatory releases made predominantly to the northern estuaries and with minimal flows to the Everglades. Current Lake Okeechobee water levels fluctuate between 10 and 17 feet NGVD based on rainfall conditions and water demands in the watershed. The boundary of the lake is now fixed, so prolonged high lake stages cause adverse impacts to the lake's littoral zone. Changes in inflows to the Central Everglades or water conservation areas, the red line on this graphic, reflect the impacts of upstream rainfall, diversions to tide, and water management operations in the Everglades agricultural area. Under pre-drainage conditions, average annual inflows to the Central Everglades rose more gradually, reaching a clear peak at the end of the wet season in October, then gradually receded throughout the dry season until the beginning of May. Under current conditions, average annual inflows to the Central Everglades tend to rise more rapidly than the pre-drainage estimate, reaching a more distributed wet season peak and then recede much more quickly through the early dry season. This leaves limited availability of dry season inflows before the start of the next wet season. Note that both the average annual flow patterns predicted by the Central Everglades project and the full SERP simulations follow the same basic wet season pattern as current conditions, but show strong improvements in the dry season flows that extend recessions. Surface water timing in the Southern Everglades, blue line on this figure, tends to maintain more consistent pattern for both the average annual pre-drainage and current conditions. This is likely due to the overland flow processes that tend to smooth out flows timing. Both the pre-drainage and current average annual flow patterns in the Southern Everglades gradually rise to a peak in October and recede more uniformly through the dry season. The Central Everglades and full SERP simulations tend to diverge more in this location since the average flow volumes are much larger under the full SERP due to the additional infrastructure that delivers flow from an eastern flow path which captures seepage and returns flows south of Tamiami Trail. The average annual pre-drainage flow volumes into the Central Everglades, the red line, are estimated to be approximately 800,000 acre-feet higher than the current average annual flows, with most of this difference reflected in lower dry season flows. Note that this annual flow volume difference is comparable to the average wet season regulatory releases from Lake Okeechobee to the northern estuaries. In other words, the reduced flows are largely the result of diversions to tide. Average annual pre-drainage and current flow volumes into the Southern Everglades, the blue line, show a similar reduction of approximately 1.2 million acre-feet, with shortfalls in both the wet and dry seasons. The average annual spatial pattern of overland flow reflects the greatly reduced spatial scale of the wetlands from the pre-drainage to the current conditions. The flow vectors similarly show the substantial reduction in flow rates that reflect the reduced flow into and throughout the Everglades. This figure compares the higher estimated pre-drainage ground elevations resulting from thousands of years of peat accretion with the current ground surface elevations that reflect a loss of peat soils due to lowered water levels and hydro periods, as well as adjacent development impacts. Note that the major changes occur in the areas where there's been peat loss inside the Everglades agricultural area, on the western side of Dade and Broward counties, and along the Marl Prairies south of Tamiami Trail. This figure compares the pre-drainage and current water depth estimates along a longitudinal profile down the center of the Everglades. The pre-drainage NSRSM water level profile remains parallel to the ground surface, and water levels remain above the ground surface, supporting peat accretion. By contrast, the current condition with reduced surface water flows into the Everglades results in lower water depths that drop below the ground surface, resulting in peat subsidence in areas where water levels are substantially lower. The compartmentalization of the Central Everglades also causes ponding upstream of levees and drying downstream of levees, contributing to the loss of tree islands. The predicted pre-drainage average October water depths were more uniform and consistent across the gently sloping central Everglades and extended eastward to the Atlantic coastal ridge, and also show a minimal stage reduction along the lower Mall prairies adjacent to Shark River Slough. By contrast, the current average October water depths show altered patterns across the Everglades, reflecting the locations of canals and levees, and show the loss of former wetlands along the backside of the Atlantic coastal ridge. The predicted pre-drainage average April water depths again remained uniform and consistent across the gently sloping Everglades, but showed water depth reductions along the lower marl prairies adjacent to Shark River Slough. By contrast, the current average April water depths showed altered water depth patterns across the Everglades, with deep dry downs along the Atlantic coastal ridge. April water depths also show irregular ponding in the Everglades upstream of levees and extensive drying in the northern portions of each of the water conservation area impoundments. Finally, the marl prairies adjacent to Shark River Slough go completely dry, contributing to peat loss and subsidence. The Biscayne Aquifer underlying the southeastern portion of the Everglades has some of the highest transmissivity rates in the U.S. Seepage losses are particularly high along the L30 and L31 canals and levees adjacent to water conservation areas 3A and 3B and Everglades National Park. Additional seepage management will be needed as we implement later SERP projects to maintain Everglades restoration benefits and reduce flooding risks in adjacent developed areas. Paleo-environmental studies by the U.S. Geological Survey have been used to set freshwater flow restoration targets for the southern estuaries. These targets have been adjusted to reflect sea level rise scenarios. Adjusted salinity targets at key sites in Florida Bay can be used to evaluate restoration performance. The results indicate improved performance from the Central Everglades project, but additional dry season flows will still be needed. Analysis of total phosphorus trends in the water conservation areas and Everglades National Park from the 1970s to present indicated general improvement, but hotspots still persist, and STA outflows remain high. Water flows from the western Everglades are particularly problematic and indicate that substantial water quality treatment is needed. Analyses of the long-term and recent STA performance indicate that STA inflow and outflow concentrations have been decreasing. Unfortunately, STA outflows are still well above the required water quality-based effluent limit for waters entering the Everglades protection area. STA outflows must remain below 19 parts per billion of phosphorus every year and below 13 parts per billion of phosphorus in 3 of 5 years. While STA 3-4 and STA 2 are making significant progress towards these targets, the other STAs are not. South Florida rainfall is strongly influenced by the Atlantic Multi-Decadal Oscillation, or AMO, climate cycle, affecting sea surface temperatures in the North Atlantic. This produces cycles of cooler years with lower average rainfall in South Florida and warmer years with higher average rainfall and more variability. The original regional simulation model, with its 41 years of simulation, included 25 cool years, resulting in lower predicted average rainfall ranges. The updated RSM, with a 52-year simulation period, has a more balanced mix of cool and warm cycles. This updated simulation period is complete for the managed version, but is still being applied to the natural system, RSM. Recent trends in AMO and global SST suggest a return to a cooler phase temperature pattern is less likely. The implication for warmer phase becoming more dominant would result in higher and more variable rainfall patterns in South Florida, but uncertainty around tropical events, Saharan dust, and wind shear still remain. The implications of climate change and rainfall variability suggest that future CERT planning will need to focus more on increased water storage to improve South Florida's resilience to flooding and droughts. The objective of these comparisons of the pre-drainage and current Everglades hydrologic conditions was to describe the defining characteristics that work to create and maintain the greater Everglades ecosystem and how they have changed over time. Our long-term vision is to recover, given modern constraints, a natural system with the ecological functions, hydrological connectivity, spatial and temporal patterns, and diversity and abundance of species that characterize the historical Everglades ecosystem. While we recognize this new ecosystem will be smaller than the pre-drainage system, the recovered ecosystem should no longer act like a set of managed, disconnected habitats, but rather a reconnected landscape exhibiting more of the defining characteristics and resilience of the pre-drainage Greater Everglades watershed.